Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
You know, when we think about 20th century science, we almost automatically picture Albert Einstein.
Oh, absolutely.
He's the icon, right? The wild hair, the Nobel Prize. I mean, the guy literally rewrote gravity and time. He just seems like this ultimate victor, the person who cracked the code.
And for a long time, he really was. I mean, for the first half of his career, he was the revolutionary.
Right.
But there's this almost tragic second act to his life that, it often gets a little glossed over in the history book.
The Princeton years, right, when he kind of became the old guard.
Worse than the old guard.
Yeah.
He became sort of an outsider in his own field. He spent decades, literally decades, waging this intellectual war against a theory he had helped create.
Quantum mechanics.
And he was haunted by one specific part of it, a phenomenon so bizarre, so deeply counterintuitive that it really offended his entire sense of cosmic order.
And he came up with that amazing phrase for it.
He did. He dismissed it as spooky action at a distance.
Which, I mean, it sounds like something out of a ghost story.
Or a B-movie, yeah. But he wasn't talking about ghosts. He was talking about quantum entanglement. And for him, this wasn't just some technical quibble about atoms.
Yeah, it was fundamental.
It was a philosophical cage match. A battle for the very soul of physics, about the nature of reality itself.
And that's really what we want to unpack today, because this isn't just about weird little particles doing weird things. It's about the very thing that kept Albert Einstein awake at night. This idea that the universe might not be local, that it might not even be real in the everyday way we think about it, and that everything is connected in this way that just seems to defy all logic.
It really pits our intuition. And I mean, the intuition of arguably the smartest person who ever lived against the raw experimental facts of how the universe actually works.
So the spoiler here is pretty clear. The universe won.
The universe always wins.
And Einstein, in this one particular battle, lost. But how he lost and why he lost. I mean, that's a story that actually leads us directly to the technologies that are building our future.
It's an incredible story.
Yeah.
So to really get it, we need to sort of walk through that battlefield, understand what entanglement is, why it seemed to break all the rules, and then how we proved it was real.
And what we're doing with all that spookiness today.
Right. But before we get to the disruption, we have to understand what was being disrupted. We need to look at the world Einstein was fighting so hard to protect.
The classical world.
The world of Isaac Newton and James Clerk Maxwell. The physics that, just feels right. It feels comfortable.
It's the physics of common sense.
It really is. And that common sense worldview is built on two main pillars. And they seem so obvious that you don't even think to question them. The first one is called realism.
And in physics, that doesn't just mean being practical. It has a very specific meaning.
It does. Realism is the basic assumption that objects in the physical world have definite properties, whether you're looking at them or not.
The classic if a tree falls in the forest argument, or, the moon is still there even when I'm not looking at it.
Exactly that. If I take a coin and I seal it in a box, that coin is either heads or it's tails. It has a definite state. Now, I might not know what that state is, but it exists. My ignorance doesn't change the physical reality inside the box.
That seems like a pretty non-negotiable starting point for doing science, right? If things don't have definite properties, what are you even measuring?
That was precisely Einstein's point of view. He believed in an objective reality that exists independent of us. So that's pillar number one. The second pillar is locality.
Locality. This is all about the speed limit of cause and effect.
Yeah, you could put it that way. It's the principle that any object can only be influenced by its immediate surroundings. If I want to move this coffee cup, I have to touch it. Or I have to, push air against it, throw something at it.
Right.
I can't just snap my fingers here in this room and make a cup fall over in Tokyo.
Unless there's some kind of signal, some connection between them.
And that's the key. That signal has to travel through the space in between. It can't just happen magically, instantly across a distance.
And this is actually where Newton got into a bit of trouble, wasn't it? I mean, we think of Newtonian gravity as this perfect clockwork system, but it had this huge locality problem.
It did, and he knew it. In Newton's equations, gravity was instantaneous. If the sun were to just vanish right now,
Poof.
Newton's math said the Earth would instantly fly out of its orbit at that exact moment, which implies that the Earth somehow knows the sun is gone instantly across 93 million miles of empty space.
Which is, well, it's spooky action at a distance. It's magic.
Newton hated it. He called it so great an absurdity, but he didn't have a way to fix it. It worked.
Until Einstein came along.
Until Einstein fixed it. That's a huge part of what his 1905 paper on special relativity was all about. He established the cosmic speed limit.
The speed of light.
Exactly. Nothing, not matter, not energy, and crucially not information, can travel faster than light.
So in Einstein's universe, if the sun vanishes, we're fine for about 8 minutes.
We keep orbiting, blissfully unaware.
We don't know it's gone until that last bit of gravitational news arrives at light speed.
He saved locality. He got rid of the magic. He built this beautiful, sensible universe that was local, that was real, and that was deterministic. Causes always precede effects. The cosmic timeline is safe.
It's a very neat and tidy picture of reality.
It is.
And then almost immediately, he and his colleagues started digging into the atom, and they found something that threatened to just tear that entire safety net to pieces.
The quantum disruption. As soon as physicists started to describe the world of electrons and photons, they realized the rules of our big, comfortable world just didn't apply down there.
So let's take those pillars one by one. How did quantum mechanics attack realism first? This is the idea of superposition, right?
Yes, superposition. And it's a concept that directly assaults realism. It says that before you measure it, a quantum particle does not have a definite state.
And we have to be so careful with the language here because this is the first big hurdle for most people. This doesn't mean it has a state, but we just don't know what it is.
Correct. This is not the coin in the box. It is a fundamental built-in uncertainty. An electron has a property called spin. And just for simplicity, you can think of it as an arrow pointing either up or down.
Okay.
In superposition, the electron isn't secretly up or secretly down. It is, in a very real mathematical sense, a combination of both up and down at the same time.
This is described by the wave function.
The wave function describes this quantum blur, this cloud of probabilities. The particle itself has no real spin until it interacts with something.
Until you measure it.
Right. The act of measurement forces the universe to make a choice. The wave function collapses, and boom, the particle is suddenly, definitely spin up or spin down.
You can see why this drove Einstein crazy. It suggests that reality is somehow fuzzy or incomplete until an observer comes along and forces its hand. It just shatters the principle of realism.
He absolutely hated it. This is where he famously debated with Niels Bohr, asking, do you really believe the moon is not there when you're not looking at it?
It's a great question.
It is. But then the rabbit hole got so much deeper. Because what happens if you take this weirdness of superposition and you apply it to two particles at once? Well, then you get entanglement.
And this is where the second pillar, locality, starts to crumble.
This is where it gets truly spooky.
Okay, so walk us through the basic setup for entanglement.
Imagine we have a process that creates a pair of particles from a single source. Let's say a specific atom decays and spits out two electrons. Because of certain fundamental laws, like the conservation of momentum, we know their properties have to be linked. They have to be opposite.
So if one is measured to be spin up,
the other one absolutely must be spin down. They're born as a correlated pair.
They're linked.
They're entangled. And in the language of quantum mechanics, this is more than just being linked. They are no longer two separate objects. They are described by a single shared wave function, a single quantum existence.
Even if you separate them.
Even if you separate them. So we send one particle to Alice, let's say she's in New York, and we send the other particle to Bob, who's in Los Angeles.
But all this time, they're still in superposition. Neither one has decided yet whether it's up or down.
Exactly. They are both still in that quantum blur of up and downness. Now, Alice decides to measure her particle.
Okay, she looks at it. She forces a collapse.
She measures it, and the wave function collapses. She gets the result, spin up. At that exact instant, and I mean instantly, Bob's particle in Los Angeles, without anyone touching it, becomes spin down.
No signal passed between them. No little message saying, hey, I'm up, so you be down.
None. The collapse of the wave function is global. The distance is completely irrelevant. It could be New York and Los Angeles, or it could be Earth and the Andromeda galaxy. The moment Alice's result is determined, Bob's is too.
And that is the spooky action. It looks, for all the world, like information is teleporting across space.
It looks like a blatant violation of Einstein's own cosmic speed limit. It looks like the universe is fundamentally non-local.
So Einstein sees this implication in the math, and he basically decides, no, absolutely not. I need to kill this idea.
He can't accept a universe that plays that fast and loose with his most cherished principles.
So in 1935, he gets together with two colleagues and drops what is basically an intellectual bomb, the EPR paper.
Yes, Einstein, Podolsky, and Rosen.
Yeah.
And it is, without a doubt, one of the most important scientific papers ever written. Not because it was right, it wasn't, but because of how profoundly, productively wrong it was.
So what was their central argument? They weren't saying the math of quantum mechanics was incorrect, were they?
No, not exactly. They admitted that the theory's predictions, the probabilities were correct. The math worked. What they argued was that the theory must be incomplete.
That the spookiness was just an illusion, a magic trick caused by something we were missing.
Precisely. This leads directly to their counterproposal, which is usually called the theory of hidden variables.
This was Einstein's way out.
This was his escape hatch. And the best way to understand it is with the famous gloves analogy.
Okay, let's hear it.
So imagine I have a pair of gloves, a left-handed one and a right-handed one. I put each one into an identical sealed box. I shuffle them up, I mail one box to you, and I keep the other.
Right.
Now I open my box, and I see a left-handed glove. What do you instantly know about the glove in your box?
I know I have the right-handed one, instantly.
But did any spooky action take place? Did any information travel faster than light from my glove to yours?
No, of course not. The outcome was decided from the very beginning. The gloves were always a left and a right from the moment you pack them in the boxes.
Exactly. The state of the gloves was determined at the source. My discovery didn't cause your glove to become a righty. It just revealed a pre-existing fact.
And Einstein argued that entangled particles were just like the gloves.
That's it. He believed they weren't in some fuzzy superposition. He argued they carried a set of hidden instructions, hidden variables, from the moment they were created.
So when Alice measures her particle and gets up, that particle was always destined to be up. It didn't just decide on the spot. It had its marching orders from the get-go.
If that's true, then there's no spooky action. There's no FTL communication. Locality is saved. Realism is saved. The universe makes sense again.
It's an incredibly powerful and honestly a much more comfortable argument. Why didn't people just accept it? Why did Niels Bohr and the quantum camp push back so hard?
Because Bohr was a purist about the theory. He looked at the equations of quantum mechanics and said, there are no hidden variables in this math, so why are you trying to add them? He believed you had to take the theory at face value. The particles really are undefined until measured.
He famously told Einstein to stop telling God what to do.
He did. But for decades, this was just a war of words. It was pure philosophy. There was no experiment you could do to, crack open an electron and look for a hidden instruction card inside.
It was an impasse. For, 30 years? You were either on Team Einstein or Team Bohr, and it was basically just a matter of philosophical taste.
It was a complete stalemate. Until 1964.
Enter John Bell.
John Stuart Bell, a physicist from Northern Ireland, working at CERN. And he's the guy who managed to drag this argument out of the philosophy department and into the physics lab. He turned it into arithmetic.
He was actually sympathetic to Einstein's view, wasn't he? He wanted to see if hidden variables could work.
He did. He wanted to find a way to make it work. But in the process, he found a way to test it.
So how on earth do you design a test for something that is, by its very definition, hidden?
That's the genius of it. You don't look for the variables themselves, you look at their consequences. You test the correlations.
Okay, this is Bell's theorem. It's famous, but notoriously tricky. Let's try and unpack it. How does the math set a trap for these hidden variables?
Okay, let's go back to Alice and Bob. But this time, instead of just measuring spin as up or down, let's say they can measure it at a few different angles.
Yeah.
Let's pick 3 angles for their detectors. Setting A, setting B, and setting C.
Okay, so 3 possible questions they can ask their particle.
Exactly. Now, let's assume Einstein is right and the particles are like the gloves. That means each particle leaves the source carrying a hidden instruction card that tells it how to answer for every possible question.
So a card might say, if asked A, say up. If asked B, say down. If asked C, say up.
Precisely. A pre-written answer for every possible measurement. Now, Bell's insight was this. If those pre-written instruction cards exist, then just by simple logic and statistics, there is a strict mathematical limit to how strongly Alice and Bob's results can be correlated when they choose their settings randomly.
It's like a probability limit.
It's a logic limit.
Yeah.
Think about it with a simple example. If you survey a population about 3 yes-no questions, do you like coffee, tea, and juice?
Yeah.
There are mathematical limits on how the answers can overlap. You can't have 80% like coffee, 80% like tea, and have only 10% who like both. The logic doesn't work.
I see. There's constraint.
There is a constraint. Bell wrote it down in a formula, an inequality. Any theory based on local pre-existing properties, any hidden variable theory, must obey this inequality. The correlations cannot be stronger than a certain amount.
So Bell's inequality becomes the test. You run the experiment thousands of times with random settings. If the correlation rate stays below that limit, Einstein and his hidden variables could still be right.
Correct. But here's the kicker. The established theory, quantum mechanics itself, predicted something different. It predicted that entangled particles would coordinate their answers better than the hidden instruction cards would allow.
They would be more in sync than the gloves could ever logically be.
Yes. Quantum mechanics predicted the correlations would be so strong that they would violate Bell's inequality.
Which would mean?
It would be mathematical proof that there are no pre-written instruction cards. It would prove the particles are making up their answers on the fly in perfect, spooky coordination.
So Bell designs the trap in '64. But the technology to actually build the trap and run the experiment didn't exist yet.
Right. We had to wait for lasers, for fast electronics. We had to wait until the early 1980s for a French physicist named Alain Aspect.
The Aspect experiment in 1982, this is the moment of truth.
This is the smoking gun. There had been some earlier attempts that were suggestive, but they all had potential loopholes, little ways that Einstein's view could sneak back in. Aspect designed an experiment to be as watertight as possible.
So he generated pairs of entangled photons, sent them off to 2 detectors. What was the crucial addition?
He introduced ultra-fast switches that could change the measurement angle, the setting, while the photons were in mid-flight.
Why is that timing so incredibly important?
It's to close what's called the locality loophole. The fear was, what if the detectors could somehow communicate with each other? Or what if the particles could somehow know in advance what setting they were going to be measured at?
A kind of conspiracy between the particles and the detectors.
Exactly. But Aspect switches changed the settings in a few nanoseconds. It happened so fast that by the time a photon arrived at Alice's detector, there hadn't been enough time for any signal, even one traveling at the speed of light, to get from Bob's detector to Alice's to tell it what setting Bob was using.
So there is absolutely no way for the particles to coordinate their answers beforehand using any known physical signal. They have to decide what to be right now in the moment.
That's it. Scrap was set. So what was the result?
The billion-dollar question.
The result was that Bell's inequality was shattered. It wasn't even close. The correlations were far, far stronger than any local hidden variable theory could possibly explain. They matched the predictions of quantum mechanics perfectly.
So the gloves analogy is wrong. The instruction cards don't exist.
They do not exist.
Are you saying?
Einstein was wrong. And, I mean, it's a monumental conclusion. Locality, in the classical sense that he cherished, is dead. The universe is fundamentally, irreducibly non-local. The state of a particle right here is, in some deep way, instantaneously connected to the state of another particle way over there.
That is just, it's a hard pill to swallow. I'm sitting here, you're sitting there. We feel very local, very separate.
We do. And that's why, even after Aspect, scientists are so cautious. They spent the next 30 years designing even more sophisticated experiments to close every other conceivable loophole.
Right, like maybe the detectors aren't efficient enough, or maybe the random number generators aren't truly random.
All of that. And then in 2015, a series of loophole-free Bell tests were finally performed that closed all the major loopholes simultaneously. The results were the same. Rock solid. The universe is officially weird. Deal with it.
Okay, let's deal with it. We have to really dig into what this means, because the moment you say instantaneous connection, the first place everyone's mind goes is faster than light communication. Mm-hmm. They think, great, we can build an Ansible, a subspace radio, I can have a real-time conversation with someone on Mars.
And this is where I, unfortunately, have to be the buzzkill. You absolutely cannot use entanglement to send a message faster than light.
But why not? I mean, it seems so obvious. If I poke my particle here and your particle wiggles instantly over there, isn't that a signal? A 1 or a 0?
It seems like it should be, but nature has this incredibly clever failsafe built in. It's called the no-signaling theorem, and it's what preserves causality. The problem, in a word, is randomness.
Okay, let's go back to Alice and Bob. Alice wants to send the bit 1 to Bob. How does it fail?
Okay, Alice has her particle A. She decides, I'm going to measure it now, and that will be my signal. So she measures it. She gets, let's say, spin up.
And instantly, Bob's particle B, becomes spin down.
Correct. So Bob could measure his and see spin down. But here's the catch. Alice couldn't force her particle to be spin up. The outcome of her measurement is fundamentally irreducibly random. It's a 50-50 quantum coin flip. She has absolutely no control over the result she gets.
So she can't control the message she's sending.
She can't encode any information into it. And now look at it from Bob's side. He's just sitting there in Los Angeles measuring his particles. He gets a stream of results. Down, up, down, down, down. It's completely random.
Right, it just looks like noise.
It is noise. How does he know that the down he just measured was because Alice just measured an up? He has no way of knowing. He has no baseline, no context. A random string of bits contains zero information.
The only way he'd know it wasn't just noise is if they compared their notes later.
Exactly. Alice has to pick up the phone, a normal, slower-than-light phone, and call Bob and say, hey, at 12.80, I got up. And Bob looks at his logbook and says, wow, at 12.801, I got down. It worked.
But the phone call itself travels at or below the speed of light.
And that's how causality is saved.
Yeah.
The spooky correlation is real, and it's instantaneous. But the information you can extract from it can only travel the old-fashioned way. Nature lets non-locality exist, but it cloaks it in randomness so you can't use it to break the timeline.
That is unbelievably clever. It's like the universe has its cake and eats it too. It's weird, but it's not paradoxical.
It prevents those kill-your-own-grandfather paradoxes. If you could send a signal faster than light, you could send a message into your own past. And then the whole structure of cause and effect just dissolves.
We should probably also quickly bust the other big myth that always crops up with this stuff.
The consciousness myth.
Yeah, the idea that it takes a conscious human mind and observer to collapse the wave function.
Ah, yes, the sort of New Age interpretation of quantum mechanics. It's a very romantic idea that our minds shape reality.
But the physics doesn't really support that, does it?
Not at all. A measurement in physics isn't about consciousness, it's about interaction. Any interaction with a large classical system is enough to cause a collapse.
So if an entangled photon hits a piece of photographic film and makes a silver halide molecule change state, that's it. Collapse over.
That's the measurement. It doesn't matter if a human develops that film and looks at the spot 100 years from now. The collapse happened at the moment of that physical interaction.
So my cat is a valid observer. My toaster is a valid observer.
If your toaster interacts with a quantum system in a way that records its state, then yes, your toaster is a perfectly valid observer.
Okay. So we've set the ground rules. No faster than light radios, no mystical mind control. But the amazing thing is we've moved past just staring at this in wonder. We're actually building things with it. We are entering the age of quantum technology.
This is the really exciting part. We've pivoted from, is this real, to, okay, it's real. Now what can we do with it?
So let's start with the one that sounds like it's straight out of science fiction. Quantum teleportation.
It's a terrible name.
It is, isn't it? It immediately makes you think of Star Trek. Beam me up, Scotty.
And we have to be very clear. We are not disintegrating a person in one place and reassembling them somewhere else. We're not moving matter at all.
So what exactly is being teleported?
We are teleporting the quantum state of a particle, the complete set of information that defines that particle.
How is that different from just, scanning it and emailing the data?
Because of another weird quantum rule called the no-cloning theorem. It states that it is fundamentally impossible to create an identical copy of an arbitrary, unknown quantum state.
You can't just quantum photocopy something.
You can't. The moment you try to measure a quantum state to get all the information needed to make a copy, you inevitably disturb it. You destroy the original.
So you can't make a backup. You can only move it.
Right. And that's what teleportation does. So here's the setup. Alice has a particle whose state she wants to send to Bob. Let's call her message particle. She also has one particle from an entangled pair that she shares with Bob.
Okay, so Alice has two particles in her lab, the message, and her half of the entangled link. Bob has the other half.
Correct. Alice then performs a special kind of joint measurement on her two particles. It's called a Bell state measurement. In essence, she entangles her message particle with her half of the link.
And according to the no-cloning rule, that has to destroy the original state of her message particle.
It does. The information vanishes from Alice's location. But because of that spooky link, the state of Bob's particle way over in his lab instantly changes. It becomes a scrambled version of Alice's original message.
Why scrambled?
It's sort of locked. Bob needs the key to unscramble it, and the key is the result of Alice's Bell measurement. So Alice sends that result. It's just 2 bits of regular classical information over a normal fiber optic cable to Bob.
So Bob gets these 2 classical bits, he performs a corresponding operation on his particle to unlock it, and then
his particle becomes an exact replica of Alice's original message particle. The state has effectively jumped from Alice's lab to Bob's. The physical particle didn't move, but its quantum identity did.
That's amazing, and we're doing this for real.
Oh yeah, routinely in labs. Back in 2022, a team achieved it over a 44-kilometer fiber optic network. We are literally building the foundations of a quantum internet, where fragile quantum information can be moved around without ever having to physically travel through the intervening space.
Which leads us right to the application that everyone is either terrified of or incredibly excited about: quantum computing.
Right. This is the big one, and it relies on both superposition and entanglement to do its work. Your laptop, my phone, they all run on classical bits.
A bit is either a 0 or 1, on or off. Simple.
But a quantum bit, or a qubit, can be in a superposition. It can be a 0 and a 1 at the same time. But the real exponential power comes when you entangle them.
Okay.
If you have 1 qubit, you have 2 possible states, 0 and 1. If you entangle 2 qubit, you don't have 2 plus 2. You have 2 to the power of 2. You have 4 states that exist simultaneously in this shared quantum space. 3 entangled qubits gives you 8 states.
So it scales exponentially. If you have, say, 300 entangled qubits.
If you have 300 perfectly stable entangled qubits, you can represent more simultaneous states than there are atoms in the entire observable universe.
That number is just impossible to comprehend.
It is. And it means a quantum computer doesn't solve problems by brute force, trying one answer after another. It sets up this massively complex quantum state, this interference pattern, where all the wrong answers are programmed to cancel each other out, and the right answer is amplified.
It's like finding the needle in a haystack by making all the hay instantly vanish.
That is a fantastic analogy, yes. And this isn't just theory anymore. In 2023, Google announced they had achieved quantum advantage, using their Sycamore processor to do a calculation in seconds that they estimated would take the world's most powerful classical supercomputer something like 47 years.
And that's why all of our current encryption is potentially in jeopardy.
A lot of it is yes. Modern encryption relies on mathematical problems that are incredibly hard for classical computers to solve, like finding the prime factors of a gigantic number. A large-scale quantum computer could, in theory, slice through those problems like a hot knife through butter.
So entanglement creates the threat, but it also provides the shield.
It does. Which brings us to quantum cryptography.
Or QKD, quantum key distribution.
And this is probably the most mature and commercially available quantum technology right now. It uses the weirdness of measurement, the observer effect, as the ultimate burglar alarm.
So how does it work?
It's quite elegant. Alice and Bob want to create a shared secret random key for encryption. They can do this by sending a stream of entangled photons over a fiber optic cable. Now, let's say a Skye, we'll call her Eve, tries to tap into that cable to read the key.
To read the state of the photons, she has to measure them.
And the moment she measures a photon, she forces its wave function to collapse. She fundamentally alters its state. She leaves a trace.
She breaks the delicate entanglement.
Exactly. When Alice and Bob are done, they can publicly compare a small random sample of their key bits. If there's an eavesdropper on the line, they'll find a higher than expected error rate in that sample.
The errors are Eve's fingerprints.
You cannot observe a quantum system without disturbing it. That's a fundamental law of physics, which means you cannot wiretap a quantum channel without being detected. The laws of nature themselves guarantee the security.
And this is already being deployed.
Oh, yeah. Banks are using it for secure transactions between data centers. And most famously, China launched the Musha satellite, which can beam entangled photons down to ground stations thousands of kilometers apart, creating unhackable communication keys from space.
It's just incredible to go from Einstein calling it spooky action in 1935 to using that same spookiness to secure global financial networks. It's a breathtaking pace.
It just goes to show you that even the most abstract, philosophical, what is reality debates in physics can end up completely transforming technology and civilization.
But speaking of those philosophical debates, they're not over. We may be using the technology, but we still argue ferociously about what it all means.
The measurement problem. We have the math, and it works perfectly. We can build machines with it. But the story we tell ourselves about what the math is describing, that is still very much up for grabs.
These are the interpretations of quantum mechanics. Let's touch on the main contenders. First, there's the standard textbook one, the Copenhagen interpretation.
Right. This is essentially the view of Niels Bohr and his group. And it's very pragmatic. It basically says, shut up and calculate. The wave function isn't a real thing. It's just a mathematical tool that tells us the probabilities of our measurements. Reality is created in the act of measurement. Don't ask what was there before.
It works, but it feels a little unsatisfying, like a cop-out.
Too many, yes. Yeah. It leaves the concept of measurement as this magical, undefined thing that sits outside the theory.
Which leads to the one that, well, it either sounds brilliant or completely insane, the many worlds interpretation.
Proposed by Hugh Everett in 1957. He looked at the math and asked a very simple question. Why do we have to add this messy collapse part to the equations? What if the wave function just never collapses?
But if it never collapses, how do we ever get a single definite result? I measure the electron and I see up, not a blur.
Everett's answer was that the wave function just continues to evolve smoothly. When you, the observer, interact with a particle that's in a superposition of up and down, the entire universe, including U-splits.
It branches.
It branches. In one branch of the universe, there's a version of you who just measured up. And in another completely separate branch, there's another version of you who just measured down.
And both of these branches, both versions of me, are equally real.
Equally real. So in the entanglement experiment, there's no spooky action. When Alice measures her particle, the universe splits. In the Alice measured up branch, Bob is now correlated to measure down. The correlation is just between the different branches of this universal wave function.
It saves locality, but at the cost of creating an infinite number of parallel universes every single nanosecond.
That's the trade-off. It's a very high price to pay ontologically. But a lot of physicists love it because the underlying math is so clean and elegant. There's no arbitrary collapse rule.
And just when that seems like the weirdest it can get, there's a newer, even wilder idea that tries to connect all this back to Einstein's other great theory, gravity. ER equals EPR.
This is right at the cutting edge. For a century, we've had these two pillars of modern physics. Quantum mechanics, which describes the very small with things like EPR and entanglement, and general relativity, which describes the very large gravity spacetime, and they just do not get along.
Their mathematics are incompatible.
Totally. But EPR is a conjecture that suggests maybe there are two sides of the same coin.
So ER stands for?
Einstein-Rosen bridge, which is the technical term for a wormhole, a tunnel, a shortcut through the fabric of spacetime.
And EPR is the entanglement paradox we've been talking about. So the theory is that entanglement and wormholes are the same thing.
The conjecture is that the spooky connection between two entangled particles is a microscopic wormhole connecting them.
A literal physical tunnel through spacetime.
A tiny, non-traversable quantum scale one, yes. And if this is true, it has a staggering implication. It implies that spacetime itself, the very geometry of our universe, might be an emergent property. It might be literally stitched together by a vast network of quantum entanglement.
So spacetime isn't the stage that the play of physics happens on. Spacetime is the play. It's the actors holding hands.
That's a beautiful way to put it. If you could somehow remove all the entanglement from the universe, spacetime itself might just dissolve into an unstructured mess. The concept of distance might be the illusion, and entanglement the deeper reality.
That brings us full circle right back to Einstein's nightmare. He was terrified that entanglement meant the breakdown of locality, the breakdown of the clear separation of space.
And he might have been right, but in a way he never could have imagined. Entanglement doesn't break space. It might actually build space. The very thing he hated most might be the glue that holds his own theory of gravity together.
That is the ultimate cosmic irony.
It really is. And it's a profound reminder that the universe has absolutely no obligation to conform to our common sense. It's random, it's non-local, and it's interconnected in ways that we're only just beginning to grasp.
It really suggests that separation is the illusion. I mean, if everything in the universe erupted from a single point in the Big Bang,
then in some sense, everything was entangled with everything else at the very beginning. We are, in a very real physical way, all part of a single vast quantum system.
Now that is a thought that will keep me up tonight.
It should keep us all up.
We have gone from a simple analogy about gloves and boxes to the fundamental fabric of reality itself. I think my brain needs to cool down for a bit.
I think we all do. It's a lot to take in.
Well, thank you for being our guide through this quantum wilderness. It's been fascinating.
My pleasure. It's the best story there is.
And to all of you listening, we'll leave you with that thought. What if distance is just a stubborn illusion? Keep questioning reality. We'll see you on the next one.